So yes, today I'll be walking you through some. I'm not the first one to talk about ambient mesh or eBPF today, but we're going to take this opportunity to dive a little bit deeper into some of the internals behind how they work, just kind of as a curiosity's sake, and also just to kind of get an idea of like the future direction of the project. Um, yep, you've got me today. A little bit about me. I've been a solo now for a handful of years. I've been, worked on our Edge API gateway built on top of Envoy proxy, and then I did some work championing a project internally, building GraphQL filter into Envoy for our platform, and most recently, as Lynn mentioned, did some work on the ambient mesh in particular, like testing support for EKS. So been very much involved in the product and on the technical side of things. Um, yeah. So just to get into it, a lot of the stuff that we're going to be talking about today kind of builds on these technologies. I imagine if we're all sitting here today, we've already heard of these, but just to kind of quick recap or, make sure we're all on the same page. First, I'll start with IP tables. IP tables is a user space Linux program that allows you to configure like kernel level firewall firewall rules. It's the technology that kind of underpins like in Kubernetes itself, like the cluster IP Kubernetes service. You use it to create those virtual cluster IPs that can be reached under the covers. In Istio, it's used often to handle the redirect so that when pod A tries to talk to pod B, you still use the original pod address, but we redirect to both the sidecar, both on source and destination using IP tables. And yeah, that's IP tables. eBPF, different technology, kind of used in a very similar way. So eBPF is a set of Berkeley packet filter extensions. It's a bunch of extension hooks in the operating system kernel that allow you to like inject your own custom logic into the kernel itself. Obviously, the kernel is a very critical piece of your hardware and kind of requires heavy permissions. To make sure that this is safe, there's a lot of restrictions built into eBPF. So by that, it means it's not a Turing-complete language. We need to make sure that it can terminate. So you can't just do like anything you want in eBPF in the kernel, but it is powerful enough to also do the redirecting rules similar to IP tables. We'll talk about very high level briefly sidecar acceleration, but it does allow us to basically map socket communications and skip things like IP tables and get more performance out of our mesh. So like high level background, IP tables, and eBPF, we cover that there. Yeah, so we just heard literally last talk about ambient, so I don't have to go too deep into ambient mesh and the Sidecarless architecture, but as Will had mentioned before, Istio today, or the traditional model is the sidecar model, so every single microservice in your cluster gets an Envoy sidecar, and those sidecars talk and do the communication, get their own certs. There's optimizations being built in. Those optimizations are the Sidecarless architecture. Most of the resource utilization and gains come from allocations. So the communication, basically, the fundamental change is we're separating L4 and L7 into different proxies. So the usual value prop of a service mesh is zero trust communication, right? So MTLS node to node is all just L4 communication. If we can put that all in these Z-tunnel proxies, so on the left, you'll see the sidecar model where you have a bunch of envoys and those envoys handle L4 and L7. And on the right, you see the two different modes. The top one is just Z-tunnel to Z-tunnel. So you'll see all those containers. They all share that per node Z-tunnel proxy, which in today is Envoy. And it talks to the other Envoy on the other Z-tunnel, but it's just doing L4. L7, like the HTTP parsing, is the most expensive part of doing communication in the mesh. So the optimization here is by just not doing it, we get a lot of performance gains. And in fact, in the bottom, when we talk about the waypoint proxy, we split L4 and L7. If you want to apply L7 policy in ambient, that policy is enforced in this waypoint proxy. And that waypoint proxy is the one that runs on your node or not, perhaps, but it runs per namespace or per service account. And it's the one that enforces authentication, header-based routing, like anything at the L7 level or layer. and an astute observation would be that waypoint proxy might not live on the node, right? So is this going to be a lot slower because you have to make an extra network hop? And this is part of the reason why we see both of these modes existing for a little while, but we do think this could actually be a performance gain in the long run. The reason being that most cloud networks are very, very fast, and most of the time is spent doing the L7 parsing twice, once on the sidecar that was going out and once on the sidecar that was coming in. But if we just do it once in an external waypoint, we haven't iterated that far, Ambient's not that mature yet, but it's theorized that it actually might be quicker because we only do L7 once. So that's kind of like the future vision of Ambient, where we are today, where it's headed. I think I didn't even mention it further, but yes, this all works under the covers with similar those IP tables and eBPF that we were just discussing. The way that those technologies were implemented, original source and destination IPs are preserved, which is important because it allows ambient Istio or just upstream Istio to work with Cilium or other network policy on the original IPs. Okay, going quickly. eBPF acceleration. I mentioned this already briefly, but it's another optimization, recent in the service mesh space to optimize connections. The idea is to bypass the TCP-IP stack, which I think is best demonstrated by this diagram here, which I hope is big enough. But on the left, you see the current sidecar or even non-sidecar model. But basically, if you use IP tables, you get what's on the left. And you'll note that you go through the socket and you run the IP tables rules on the way in and out when redirecting to yourself, when you could just map socket to socket, because we're not doing anything to manipulate that request. We just want it to go elsewhere first. eBPF acceleration has some limitations. Number one, it requires Linux kernel 5.7 or newer. So you got to make sure your infrastructure supports it. You got to get this proved in your organization, security posture. Good news is that we can fall back to IP tables. eBPF acceleration, well, I'll talk about that more in a second. So now I want to tie this into kind of like the cloud and how things are set up today, and again, moving towards the future. So we mentioned IP tables. When you install Istio today, either in a sidecar or ambient mesh architecture, you usually get an Istio init container that starts up on every pod, and that init container writes these IP table rules into like the pod networking namespace and handles the redirect for you. This requires elevated permissions. IP tables is not like is a program that you don't just want anyone to be able to run. To support another alternative that doesn't require elevated pod permissions, even in an init container, Istio added support for an Istio CNI, which can replace the init container. This Istio CNI is, perhaps I'll talk a little bit about CNI for those who haven't heard it before, but it's the container network interface. It's an abstraction built into Kubernetes itself that allows you, it's like a hook that lets you set up the network for pods that communicate to each other. So if you are on EKS or GKE or any of these other platforms, every time a pod starts up, you make a call out to the CNI. There are 3 parts of the spec. It's literally just create, add, and check, or create, delete, and check. So you're just creating like a net pod, like IP networks namespace. You can delete it, which is basically creating or deleting IP tables rules, and check that like what you asserted is there and exists. But this is all implementation specific. So like GKE has its own CNI, EKS has its own CNI. They're implemented differently. That means that like Istio has to build on top of that CNI. CNIs can be chained. They can be like plugins. It's like an arbitrary binary that you can execute like as part of this interface. And so again, just part of Kubernetes, like this pod spins up, you call it CNI. It'll set up the initial networking namespace with like EKS CNI or GKE CNI, and then Istio CNI on top of it can just also do the IP tables rules there. That's like the really quick version. Additionally, the Merbridge is a project out for Istio that can also do the like the same redirect that IP tables does as a CNI, but using eBPF. There's some limitations with Merbridge today. I believe most of the Istio feature set is supported, but there's some corner cases. I think some stuff with IPv6 that don't work exactly as you'd expect. Building on that, yeah, each CNI needs to be validated so that, that it works with others, because the IP tables rules are selecting certain devices like in your pod networking namespace. if you need to rewrite the rules sometimes depending on the CNI. That's why like testing for ambient EKS and GKE was important and different. The rules aren't identical for IP tables. And there is other platform specific logic for Istio that's built in today and will need to be updated for ambient in the future, which we're going to follow up on right now. Okay, so yes, what's left? Like future work towards like ambient. It seems like we've got ambient mesh. We're at the point of optimizing, right? Like we're trying to cut back resources. Things work. Maybe it's not ideal, but we're optimizing. eBPF feels like a really extreme optimization. If we're at the point of optimizing, like, are we already done? But no, we got a lot left to do. So before I get into one of the parts of Istio we want to change for ambient, I want to talk a bit about certificate management and how it works today. So Istio, it's MTLS with Istio as a CA. When you deploy Istio, Istio-D is the one that's creating the MTLS cert, like signing the MTLS certs for communication across pods. When you install Istio by default, it usually generates its own self-signed certificate and uses that certificate locally to then sign CSRs. You can replace this with an external CA. So there's an API in Kubernetes where you can just add an extension hook or point. Istio-D will delegate the signing to an external cert manager, for example. So that's like the right. The left is kind of default. Istio, if we move towards ambient, should really support all of the modes, including itself as a CA, which is what we're going to get into. Also, we've got the way that the Istio-D self-signed CA works today is it uses the token request and token review API in Kubernetes. So for those who haven't heard of this before, there is an API for a specific service account. You can request a JOT, like a JOT that proves to Kubernetes, to others, that you are this service account. And then you can also get that reviewed. And so there's, in the diagram at the bottom here, the way Istio uses this API is, there's Envoy. It runs next as a sidecar to your pod. There's the Istio agent, which is the one that will then request. It handles SDS and the SDS, which is secret discovery, and then XDS, all of the other Envoy config requests. So when you want a new cert, Istio agent goes ahead and makes a token request to the Kubernetes API server. It says, hey, I am microservice foo. I am service account foo. I want a JOT that proves that I am foo. And then you sends that JOT to Istio-D when it wants a cert signed. It'll generate a signed cert locally, use that cert, like keep it private, but send the public cert to be signed with the JOT that says, hey, I'm proving that I am foo. Istio-D will then get that token reviewed by the API server and then sign that cert. The important thing to note here is that the Istio agent is per pod. So, in the sidecar model, the Istio agent is, one per pod. So if we think about certificate management in ambient, we're kind of changing the model a little bit. When Istio was initially built, there was an implicit assumption that, there's one service account for one Envoy, for one MTLS cert that gets signed by Istio-D in a default installation. And on the right, you'll see, well, now that today the Z-tunnel proxy is per node, right? So it's sharing multiple tenants behind. So when it's requesting to Istio-D, it might want MTLS certs for either service account app foo or app bar. It really needs both. And this is kind of a fundamental change in how Istio had worked before. The way that ambient works today is it impersonates the kubelet because the security posture of the Z-tunnel is basically the same as the kubelet. The kubelet has, domain over everything on its node, and so does the Z-tunnel. The Z-tunnel can proxy anything on its node. The security posture is relatively the same. And impersonation is supported in that token review, token request API. Now, the problem, where we're getting back into platform-specific things, is impersonating the kubelet is possible on GKE, the way the kubelet was configured. GKE is owned, the kubelet is owned by GKE. In EKS, it uses IAM for authentication. We can't just impersonate it. So there needs to be changes to the Istio-D certificate model so that we can support, and this is like future up and coming work. Right now, it works. I'll talk about how it works. Right now, it works on EKS because the Z-tunnel has admin permissions. but that's not the long-term solution, right? This is permissions for we're going to limit those permissions, and the way that we can do this is the Istio agent will then make requests, would send two SPIFFE IDs. So SPIFFE is like the technology behind like the certificate request and approval from an Istio D. Instead of just saying I want service account foo and saying I am service, like I'm proving I'm service account foo and I want the cert for foo, it's gonna say I am the Z tunnel and I want service account foo, and we'll verify that it is the Z tunnel, and then Istio D will also verify that the service account it wants exists on the node. And so Istio D is going to have to be updated a bit to watch the like the pods on a node, so that it can, when it verifies the Z tunnel comes, it can issue the cert rather than relying on impersonation, which isn't really cross-platform. So again, like you can test all these things, they work, but Ambient's still up on the rise. So yeah, we went into one technical thing, but what else is left, right? Like, Ambient is improving. We're benchmarking. We're already seeing significant gains, and a lot of these things are getting things tech or production ready. The future of Ambient and eBPF in the cloud. Well, let's start with HTTP 3. When we think about the Z tunnels communication, it's basically, I think the terminology was HBone. It's like using an HTTP-based overlay network, and it's implemented by using HTTP Connect, HTTP2 in particular right now. All the Z tunnels are Envoy. Envoy, when it gets support for HTTP 3 Connect, which is mask, then we'll get additional performance benefits. HTTP 3 is better in networks that drop more packets. If we think about the progression, I think there's a talk later today about HTTP 1, 2, and 3, so we'll get really deep into it. But HTTP 1 to 2, the big change was multiplexing. You can reuse a connection, multiplex. From 2 to 3, moving from TCP to UDP, and not getting the connection stuck on a dropped packet on any of the connections is the big improvement, right? So packet loss is less painful. That's coming to Z-Tunnel. Secondly, and I think this was touched upon by Will right before, but Z-Tunnel is moving to Rust, currently Envoy. So I think we will also cover the benchmarks. They look a lot better. The RAM usage in particular, at 20K pods, the RAM usage was 20 times more with no pods on Envoy and 20 times less on Rust without. And in particular, the reason why is because the abstractions that Envoy has built in are not great for what the Z-Tunnel is trying to do. So the way it's implemented today in Envoy with the Z-Tunnel is we have like an internal listener that routes back to itself, so they can have a tunnel, like it can tunnel out. And that means that it has like a cluster per cert. And the really short version is an n-squared configuration problem. You add a ton of pods and the configuration gets really large. But Z-Tunnel will be different, and not Z-Tunnel. The Rust proxy will have a different API, which should resolve that. Yes, updating the Istio CA. So platform-specific needs. Already mentioned a little bit about some of the certificate management in Istio today. So platform updates for things like EKS, but also, that new XDS Z-Tunnel API. And then last, like optimizing eBPF redirect. So most of the Ambient iterations today are making use of IP tables. There's some groundwork that's being done on Ambient, but those redirect rules are different, or not Ambient, eBPF. So that rules need to be, flushed out. And I think I've covered everything.